Hi, welcome to Algebra 2 Common Core. In Algebra 2, we have been talking about different types of functions. For example, we could categorize functions as linear functions or as quadratic functions, and we're going to see quite a few more types of functions that exist. Today we're going to talk about another way to categorize functions. Functions can either be even functions or odd functions. And we'll see that there are some functions also that are neither even nor odd. So let's start out with our definition of an even function. A function is classified as even if, when I find the function value at negative x, it turns out to be exactly the same function value as f of x. So f of negative x is equal to f of x. And that has to happen for every value of x in the domain for the function to be even. On the other hand, a function is classified as odd if f of negative x is equal to the negative of f of x. So we're going to practice quite a bit today in deciding whether functions are even functions or odd functions and why, using these two definitions. Let's begin by examining the function f of x is equal to x to the fourth plus 2x squared plus 5. We're going to look at different ways to determine whether this function is even or odd. So first of all, if I want to look numerically at this function, I'm going to make a table of values. And I'm going to evaluate this function at several different x values. And in fact, I'm going to pick x values that are opposite of each other. So for example, if I substituted 2 in for x, you can do that on your calculator. So you could say 2 to the fourth plus 2 times 2 squared plus 5. And I see that on my calculator I'm getting the answer of 29. Make sure if you don't have your calculator, you pause the video and go get it, because it's going to be really important to have your calculator for today's lesson. Now I'm going to switch my x value to the opposite, so let's try a negative 2. So substituting negative 2 in for x, and again another way of doing this on my calculator is to put the function into y1 and then use that value of y1 or look in a table of values to get the answers. Now when I try negative 2 in for x, I see that I also get the answer of 29. Now we want to try more than one pair of numbers for x to see if this is consistent. So I'm going to plug 1 in for x, and when I plug 1 in for x, I see that my output is equal to 8. Now let's try the opposite, negative 1. Negative 1 to the fourth plus 2 times negative 1 squared plus 5 also gives me the answer of 8. So we can make the conjecture that since we tried opposite x values, and those opposite x values produced the same y values, we're thinking that perhaps this is going to be an even function. Now again, all we've done is just investigated a couple pairs of points, but that gives us some good information about what kind of function we might have. Our next effort will be in looking at this algebraically. So algebraically means that I'm going to try to solve for f of negative x. I want to come up with an equation for the function when I substitute negative x in for all of the x's. So we're going to say negative x is going to be raised to the fourth power plus 2 times negative x squared plus 5. Now when I calculate this, I'm getting x to the fourth plus 2x squared plus 5. And I see that this answer for f of negative x turned out to be exactly the same as my function f of x. So that tells me that if f of negative x is the same answer as f of x, then algebraically I know that this function must be an even function. So now I've done my proof or my investigation using any random x value. Substituting in a negative x, I see that the function value turned out to be exactly the same as the original. So this gives me much more information than just doing the problem numerically. Now we're also going to take a look at the graph of this. So I'm going to have to set up my graph, so you've got a spot on your graph paper to do this as well. So I'm going to say, let's make my graph. I'm going to use the graphing calculator. So take a minute to enter that function into your graphing calculator. y1 equals x to the 4th plus 2x squared plus 5. I did a zoom number 6 to get a nice window. And I see that my graph crosses the y-axis at 5, so I'm going to show that. It looks kind of like a parabola, but I actually know that this graph is not a parabola because it's not just an x squared function. It's got an x to the 4th in it as well. So when I look at this graph, I see that this graph is actually symmetric with respect to the y-axis. I'm going to use the abbreviation WRT to stand for with respect to. That's going to be something that we're going to see quite a bit in this section. Now, if a graph is symmetric with respect to the y-axis, all that means is that when I substitute negative x into the function, I get exactly the same function out. Well, this, of course, is our definition of an even function. So again, I can see by looking at the graph that this function is even because I had symmetry with respect to the y-axis. So the y-axis is like a mirror on this function. So take a few minutes to look over all three ways of determining whether that function was even. Let's go ahead and go through that process with example B. F of x equals 3x to the 5th minus x. So I again numerically would like to test out some values for x. I want to try positive and negative values. So for example, if I substitute the number 1 in for x, I see that my answer turns out to be a 2. If I substitute negative 1 in for x, and again you could plug this into your graphing calculator under y1 and then look at your table of values, negative 1 has an output of negative 2. Let's try another pair, so how about the number 2? So when I plug that into my calculator, I'm getting 94. But when I substitute negative 2 for x, that's giving me a result of negative 94. So from this table of values, I can see that when I substituted opposite x values, the results were the opposite of the y's. So when opposite inputs give me opposite outputs, that leads me to the idea that this must be an odd function. So we're going to confirm this by looking algebraically. Let's go ahead and find the function value at negative x using this equation. So 3 times negative x to the 5th power minus negative x. Let's algebraically simplify this equation. So I'm getting negative 3x to the 5th plus x. Now how does this compare to our original f of x? If I factor in negative 1 out of both terms, I see that it's going to be negative 1 times 3x to the 5th minus x. So this is telling me that f of negative x is the answer negative f of x. So it's the negation of the f of x function. When that happens, I see that I have an odd function, according to my definition. Let's examine this one graphically as well. So making a graph. Pause the video for a minute and go ahead and make your graph for this one. First of all, let's take a look at the graph that I drew. So hopefully you got the same graph on your graphing calculator. I see that this is a function that goes through the origin, but if I examine it carefully, every point is a reflection over the origin. Now the reason for that is that when I look at f of negative x, that corresponds with a reflection over the y-axis. Negative f of x corresponds to a reflection over the x-axis. So if I reflect something over the y-axis and the x-axis, that's actually the same as reflecting over the origin. So we are going to say that this is symmetry with respect to the origin. When I have symmetry with respect to the origin, that function is an odd function. One quick little thing, I don't know if you learned this in geometry, but one way of telling pretty easily if a graph has symmetry with respect to the origin is by taking the graph and turning it 180 degrees. So basically turn your paper upside down. And if you get exactly the same picture as you had to begin with, then that's telling you that you also have symmetry with respect to the origin. So it's a quick and easy way to determine symmetry with respect to the origin. Now that we've had an introduction into the definition of an odd function and an even function, let's see how the coordinates are going to be affected based on which kind of function we have. So in example number 1, we're given a table, but the table is only partially filled out for f of x. In part A, we're told that the function is an even function. So if a function is an even function, then that's telling me that when I have opposite x values as the inputs, they are going to produce the same y's. So for example, when I look at the x-coordinate of -3, the opposite of -3 is +3. So when the inputs are opposites, the outputs are exactly the same. So that tells me that the output of -3, which is 5, is going to have the same output as 3, which is also going to be 5. Let's look at another pair. When I've got an input of 2, the output is -4. So if I take the opposite input, the output should match, and the output should still be -4. Finish it off with the number 1. When the input is -1, the output is -7. Because this function is an even function, if I take an opposite input, then the output should still match -7. If you were to plot those points on a graph, you would see that this graph would be symmetric with respect to the y-axis. And that's also a way to tell if something is an even function. Now let's look at part B. In part B, we've got an odd function. So an odd function means that when we have opposite x values, they are going to produce opposite y values. So looking at pairs that are opposite x's, when x is -3, the output was 5. So if x is +3, this time because I have an odd function, the output would be the opposite, so -5. For the number 2, the output is -4. But if I take the opposite input, the output should be the opposite, +4. Finish it off with the number 1. When I have -1 as the input, the output is -7. So if I take the opposite input, the output should be the opposite as well. And again, if you were to plot these points on a graph, you would see that this graph would be symmetric with respect to the origin, also telling us that it's an odd function. So speaking of graphs, let's take a look at example number 2, where we're given half of a graph of f of x, and we're asked to produce the other half of the graph based on what kind of function type we have. If we have an even function, remembering our definition, that means that when I have opposite inputs, the opposite inputs are going to produce the same output, so the same y value. So I could make a little table of values here for the points that I'm given, and then expand it to the points that are the opposites. So I see that I've got the point 0, 0, I've got the point 3, 5, and I've got the point 7, negative 2. Now 0 is not going to help me at all because I can't, when I take the opposite of 0, it's still 0. So let's look at the other 2 points. When I take the opposite of 3, that's going to be a negative 3, but because I have an even function, the y stays the same. When I take the opposite of 7, that's going to be a negative 7, so therefore I'm going to keep my y value the same, negative 2. So pause the video and take a minute to plot those points and connect the rest of the graph to see the whole graph that I would be given for this even function. So here's the complete graph of f of x showing that it is an even function. We identify this symmetry as y-axis symmetry, and of course we know the y-axis symmetry is an even function. Let's go to part B, where we've got an odd function now. We're given exactly the same beginning points. So I'm going to go ahead and make my table of values and then take the opposite x. When I have an odd function, then opposite x's produce opposite output. So making my table of values, I'm going to use exactly the same points that I had on the previous example. So 0, 0, 3, 5, and 7, negative 2. Now, let's create some other points that are going to be on this odd function. So if I take the opposite of 3, that'll be negative 3, but this time because I have an odd function, I'm also going to take the opposite of the y. For 7, the opposite is negative 7, so taking the opposite, I get a positive 2. So once again, pause the video, plot those points, and create the odd function that we have here for f of x. Looking at our complete graph, I see that this graph would have symmetry with respect to the origin, and that coincides with our identification of this function as an odd function. So far, we have seen functions that are either even or odd. But what we're going to find out is that some functions don't fall under either of those categories. It's possible for a function to be neither even nor odd. So let's investigate the next few examples. In exercise number 3, I've got the function f of x equals the absolute value of x minus 4. So I'm going to start by looking at this numerically. It says evaluate this function for a variety of opposite input pairs and then determine whether this function looks like it's going to be even or odd. Then we're going to go ahead and sketch this graph on the axes and see if the graph coincides with the answer that we got by looking at the table of values. So please pause the video for a few minutes, and make a table of values where you're trying out different x values, opposite x values, and determining whether we're getting the same y or opposite y. And then go ahead and make the graph and decide whether this function is even, odd, or neither. So stop the video now and do that work, and then come back and check your work with mine. Looking first of all at our table of values, when we tried opposite x values, you should have seen that the y values, the outputs, still matched. So that idea of the opposite x producing the same y tells me that this function looks like it's going to be an even function. Again, just making a table of values isn't a proof, but it is a good beginning to decide. So it's a way of investigating a function or looking at it as an inquiry. For part B, when I do the graph without using my calculator, I know that the absolute value graph is a V-graph, and because it's been shifted down 4 units, it should look like what I have graphed right here. Because this graph has symmetry with respect to the y-axis, that also leads me to believe that this is an even function. Now, we could, of course, algebraically find f of negative x, and I'm going to take 1 minute to do that. So f of negative x means that I'm replacing x with a negative x. So the absolute value of negative x minus 4. Of course, when we take the absolute value of negative x, we're just getting the absolute value of x minus 4. So if f of negative x is equal to f of x, that also proves to me that this must be an even function. Let's try exercise number 4 in the same fashion, but this time our function is f of x equals 2 to the x. So it says decide whether this is even, odd, or neither, and support your argument with numerical evidence and graphical evidence. So again, I'm going to make a table of values, and I'm going to try positive and negative values for x. So for example, if x is 1, 2 to the first is 2. If x is negative 1, 2 to the negative first, oh, that's good review, that gives me a 1/2. If x is 2, 2 to the second is 4, but remembering back to our exponents, if x is negative 2, 2 to the negative 2 is 1/4. So this is making it look like I have neither an even nor an odd, because when I take the opposite input, it doesn't give me the same output, but it also doesn't give me opposite output. Now if I go ahead and make a graph of f of x equals 2 to the x, hopefully you recall from our exponent unit that our graph of 2 to the x, our graph of our exponential, and in this case a growth function, would go through the y-axis at 1. At x equals 1, it would have a y value of 2. I could even use the table of values that I've just created. So at negative 1, I'd have 1/2. At 2, I'd have 4. And at negative 2, I'd have 1/4. So connecting these points, this is the graph of my exponential function. And clearly this graph is neither symmetric with respect to the origin, nor symmetric with respect to the y-axis. So again, that confirms the idea that this function, f of x equals 2 to the x, is neither even nor odd. I'd like you to pause the video and try exercise number 5 on your own. You're given the function g of x, and again, you're asked to fill out a table of values to determine whether this function is even, odd, or neither, and then explain your answer. Once you have your table of values, also sketch a graph using your calculator. I've given you a nice window to use for that. And confirm your idea from part A. See if your answer is accurate according to the graph as well. When you are done, please come back and check your work with what I have. Welcome back. Compare your table of values with my table of values, where I found out that when I entered opposite x values, the function produced opposite y values. So my conjecture is that this is an odd function. Let's confirm it by looking at the graph. So I used the table of values and I plotted those points, and I did see that I had a graph that had origin symmetry. And again, the easy way to figure out if that has origin symmetry is just to turn your paper upside down and see if the graph looks exactly the same. And in this case it does, so that tells me that the graph is symmetric with respect to the origin. Any graph symmetric with respect to the origin is going to be categorized as an odd function. Now we could also take a minute and do f of negative x. I should find out, oh I'm sorry, this is the function g of x, so let's find g of negative x. So when I substitute negative x in for x, I should have negative x cubed minus 4 times negative x, giving me the function negative x cubed plus 4x. This, of course, is the opposite of my g of x function. So if it's the opposite of my g of x function, that tells me that yes, without a doubt, I do have an odd function. In exercise number 6, I'm again given a table of values that's partially filled out for the function f of x, and I'm told that the f of x function is an even function. So if it's an even function, that of course tells me that opposite x values will produce the same y values. So when I have the input of 3, the output is negative 5. So when I take the opposite of the input, I am getting exactly the same output, so that's going to be a negative 5. Looking at positive 2 gives me an answer of negative 1. So when I change the input to its opposite, the output still stays the same because the function is even. Lastly, when I have the input of negative 1, the output was 3. Change the input to its opposite, but the output remains the same. So filling out the table, I know that this should be the complete table for f of x. And to finish up, we're given 3 different functions, and we want to decide, are these functions even, odd, or neither? Now for the first one, I'm going to go ahead and make a table of values like we have in the past, because that's really a good way to start out to decide whether my function is even, odd, or neither. When I substitute 1 in, I see that I'm getting an answer of 3. Substituting negative 1 in, I also get an answer of 3. When I substitute 2, I'm getting 18. And when I substitute negative 2, I'm also getting 18. Now you can think about what's making these answers the same. I, of course, am going to focus on the fact that the x has an even exponent. So when I take an even exponent on a negative number, the result turns out to be the same. But to prove for sure what kind of function I have, I should really substitute negative x into my function and see what happens. So negative x would be raised to the 4th power, and then I'd add on 2. So I find out that f of negative x is really the same exact function as f of x. So when I start out with an f of negative x and I see that it turns out to be the same, that of course tells me that I have an even function. So pause the video for a minute and you try exercise B. By examining the table of values for f of x equals 2x cubed plus x, I see that opposite inputs give opposite outputs. So that gives me the idea, the conjecture, that this must be an odd function. To prove it, I'm going to go ahead and substitute negative x in for f, and I see that I find out that f of negative x is equal to the negative of f of x. So yes, I'm correct, this must be an odd function. For my last example, I'm just going to go ahead and substitute in a negative x into my function and see what the result turns out to be. So negative x squared minus 3 times negative x. So I am ending up with f of negative x is equal to x squared plus 3x. Now if I look closely, I see that f of negative x is not the same as f of x. But I also see that f of negative x is not the same as the negative of f of x. So if neither holds true, then that means that this function must be neither even nor odd. So we've done a lot of work examining functions that are even and odd, and these concepts are going to be really important for our next few chapters when we're talking about radical functions and polynomial functions. So thank you for working with me tonight. I know this was a little bit longer of a video, but this information is really important. So make sure you understand the difference between even, odd, and neither kind of function. Have a great night. Bye-bye.